What if everything you think you know about the universe is wrong? Picture a world where gravity isn't just a force pulling you down, but a ripple in the fabric of space, time itself. Where particles can be in two places at once, connected across vast distances in ways that defy logic, where the past, present, and future might not be as fixed as they seem. These aren't just wild fantasies, they're real, groundbreaking ideas that physicists are wrestling with right now. And today, we're going to explore 36 of the most mind-bending concepts that are tearing up the rulebook of reality. Think about the last time you looked up at the night sky and felt that sense of awe. The stars, the vastness, the mystery, it's all part of a cosmic puzzle we're still trying to solve. But what if the answers we've been clinging to are just the tip of the iceberg? What if black holes aren't just cosmic vacuum cleaners, but doorways to other universes? What if time itself is an illusion, a trick of perception? These questions aren't just philosophical musings, they're the cutting edge of science, where the impossible starts to look probable. And the deeper we dig, the stranger and more wonderful it all becomes. This isn't just about abstract theories. These ideas could reshape everything from how we understand our place in the cosmos to the technology of the future. Imagine computers that harness the power of parallel universes, or communication that happens faster than light. Imagine uncovering the true nature of dark matter, or proving that we're all living in a simulated reality. It sounds like science fiction, but these are the very real frontiers of physics today. So buckle up, because we're about to take a journey through the most disruptive, paradigm-shattering ideas in science, ones that will challenge your understanding of space, time, and existence itself. And by the end, you might never see the universe the same way again. The holographic principle turns everything we thought we knew about reality inside out. At its core, this idea suggests that our three-dimensional universe, with all its stars, galaxies, and even you watching this right now, might actually be nothing more than a projection from a two-dimensional surface at the edge of space. Think of it like a movie screen. When you watch a film, the images have depth and movement, but they're really just flat pixels arranged in a specific way. Now apply that to the cosmos. What if every event, every particle, every law of physics is just information encoded on some vast, unseen boundary, like data etched onto the surface of a black hole? This isn't just wild speculation. Physicists like Leonard Susskind and Gerard T. Hooft have spent decades exploring this idea, and it solves some of the most stubborn puzzles in physics. Take black holes, for example. According to quantum mechanics, information can never be destroyed, yet black holes seem to swallow it whole. The holographic principle offers a way out. The information isn't lost. Instead, it's smeared across the black hole's event horizon like a cosmic fingerprint. Suddenly, the paradox disappears, but the implications go even further. If the universe is truly holographic, it could explain why gravity feels so weak compared to other forces. In this framework, gravity might not be a fundamental force at all, just a side effect of the way information is projected into our three-dimensional experience. Even dark energy, that mysterious force accelerating the expansion of the universe, might make more sense if we're living in a kind of cosmic illusion. The craziest part, some experiments are already testing this idea. Scientists are studying the cosmic microwave background, the afterglow of the Big Bang, for subtle patterns that might reveal whether space-time is pixelated at the smallest scales, like a digital image. If they find evidence, it would mean reality isn't smooth and continuous, but built from tiny, discrete bits of information, just like a hologram. What does this mean for us? If the holographic principle is true, then everything, your thoughts, your memories, even the device you're using right now, might just be data on a cosmic hard drive we can't see. It's a humbling thought, but also an exhilarating one, because if reality is a projection, then the rules we take for granted might be far more flexible than we ever imagined. Time might feel like the most solid, unshakable part of our reality, the steady tick of a clock, the inevitability of aging, the way we organize our lives around schedules and deadlines. But what if it's all a grand illusion? Einstein shattered our simple view of time when he showed it's not universal but relative, stretching and compressing depending on how fast you're moving or how close you are to a massive object. But some physicists now go even further, suggesting time might not exist at all as a fundamental part of the universe. Take the block universe theory, which treats the past, present, and future as equally real, like scenes printed on a roll of film. In this view, the flow of time is just a trick of perception. Your birth, this moment right now, and every event yet to come already exist in a static, unchanging four-dimensional structure. It's as if the universe is a frozen sculpture, and our conscious experience is just a flashlight moving across it, creating the illusion of movement. This isn't just philosophy. The equations of general relativity work perfectly without any need for a now, suggesting time's passage might be something our brains invent, not the cosmos. Even stranger, quantum mechanics hints that time might emerge from something deeper. Entanglement, that spooky connection where particles instantly influence each other no matter how far apart they are. Experiments show that without quantum entanglement, the very concept of causality, one event leading to another, starts to break down. Some researchers think time could be a side effect of these quantum relationships, a kind of cosmic glue holding reality together in a way that feels sequential to us. If time isn't fundamental, what happens to free will? If the future is already out there, set in stone like a page in a book, do our choices even matter? And what about cause and effect, the bedrock of science? These aren't just abstract questions. They could redefine how we understand everything from the Big Bang to the nature of consciousness. Some theories even suggest that in a timeless universe, death might not be an endpoint, just another coordinate in the block. The implications are dizzying. If time is an illusion, then the urgency we feel, the way we mourn the past or fear the future, might be based on a cosmic misunderstanding. It's a radical shift, one that challenges not just physics but our deepest human instincts. Yet it also opens doors to astonishing possibilities, like rewriting the rules of quantum computing or uncovering the true structure of reality. After all, if time is just a shadow on the wall of a deeper universe, what else are we getting wrong? The idea that our universe might be just one of countless others, each with its own unique set of physical laws, sounds like something straight out of a sci-fi movie. But the multiverse isn't fantasy. It's a serious scientific hypothesis with roots in some of the most respected theories in physics. Take cosmic inflation, the theory that our universe expanded exponentially in the first fraction of a second after the Big Bang. If inflation can happen once, why couldn't it happen an infinite number of times, birthing new universes like bubbles in a vast cosmic foam? Each of these bubble universes could have entirely different constants of nature. Gravity might be stronger in one, electromagnetism weaker in another, and some might not even have atoms as we know them. String theory takes this even further. It suggests that what we perceive as our four-dimensional universe might just be one slice of a higher dimensional reality, like a single page in an unimaginably thick book. In this framework, parallel worlds could exist mere millimeters away from us, separated by dimensions we can't see or touch. Picture an ant walking across a folded sheet of paper, what seems like a vast distance to the ant might be a tiny gap from a higher perspective. If that's true, there could be versions of reality where dinosaurs never went extinct, where you became a professional skydiver instead of watching this video, or where the laws of physics make life as we know it impossible. One of the most compelling arguments for the multiverse is the fine-tuning problem. Our universe's constants, like the strength of gravity or the mass of an electron, are so precisely calibrated for life that even tiny changes would make stars, planets, and chemistry impossible. It's as if someone dialed in a perfect combination on a cosmic lock. The multiverse offers an elegant solution. If there are infinite universes with random parameters, it's no surprise that at least one got lucky. We just happen to live in the version where everything lined up right. But how could we ever prove something so extraordinary? Some scientists are searching for bruises in the cosmic microwave background, anomalies that might show where our universe bumped into another. Others are simulating how alternate physics would play out in hypothetical worlds. And if string theory's extra dimensions are real, future experiments might detect particles vanishing into them, like marbles rolling off a table into an unseen dimension. The implications are staggering. If the multiverse is real, it means every possible outcome actually happened somewhere. Every choice you didn't make, every historical event that could have gone differently, it's all out there, unfolding in parallel realities. It challenges our deepest notions of uniqueness and destiny, but it also offers a humbling perspective. Our universe might not be special, just one flickering possibility in an endless sea of existence. And that raises a haunting question. If there are infinite versions of you, what does that say about the nature of identity itself? Quantum immortality takes the bizarre logic of Schrödinger's cat and applies it to the most personal question of all: what happens when we die? Imagine this. In the many worlds interpretation of quantum mechanics, every possible outcome of an event spawns a new universe. So if you were in a life-threatening situation, say, standing in front of a firing squad, there would always be at least one universe where, against all odds, the gun jams, the bullets miss, or some other fluke saves you. From your perspective, you'd never experience death, only an unbroken chain of survival. Your consciousness would keep branching into realities where you're still alive, while other versions of you cease to exist. It's as if the universe itself conspires to keep you perceiving, no matter how slim the odds. This idea isn't just a thought experiment. It forces us to confront the nature of subjective experience. If consciousness is like a spotlight illuminating only one path through the infinite branches of reality, then from your point of view, you'd always find yourself in a timeline where you persist. The frightening corollary: no one would ever remember dying because the moment death occurs, their awareness simply stops branching. Friends and family in other universes would mourn, but you would only ever know the realities where you survived. Critics argue this is a misinterpretation of quantum mechanics, conflating probability with perception. After all, if every unlikely survival splits reality, why don't we notice more near-miraculous escapes in everyday life? Supporters counter that we do think of those stories where someone misses a flight that later crashes, or recovers from a terminal illness against all medical odds. Could these be glimpses of the branching at work? The philosophical implications are staggering. If some version of you always continues, does that make death an illusion? What does it mean for identity if countless yous are constantly diverging? And if consciousness is this resilient, could it exist independently of the physical brain? Some theorists even speculate that quantum immortality might explain near-death experiences. Those flashes of light and tunnel visions could be moments where consciousness shifts to a surviving timeline. But here's the twist: even if this idea holds water, it doesn't grant true immortality. Eventually, in a universe as chaotic as ours, the odds of survival would dwindle to nothing. Heat death, cosmic collapse, or sheer entropy would erase all possible futures. Yet until that far-off point, the theory suggests a haunting possibility, that life, against all reason, clings to existence like a flame in the wind, flickering but never fully snuffed out. It's a concept that blurs the line between physics and metaphysics, leaving us to wonder, if reality is this fluid, what else might we be getting wrong about the nature of existence itself? Dark matter is the universe's most frustrating ghost. It doesn't emit light, reflect it, or interact with ordinary matter in any way we can directly detect, yet its gravitational fingerprints are everywhere. Galaxies spin faster than they should. Light bends around invisible masses. The cosmos behaves as if 5 times more matter exists than what we can see. So where is it all hiding? Some scientists now think dark matter isn't just a diffuse cloud, but could be organized into structures as complex as the visible universe, hidden cities of shadow where the rules of reality might be entirely different. Picture this: entire dark galaxies made of this mysterious substance, swirling in the voids between the stars we see. These wouldn't be mere clumps of particles, but intricate systems with their own dynamics: dark halos, dark filaments, even dark planets orbiting dark stars. The mind-bending part: if dark matter interacts with itself through forces we don't yet understand, these structures could have a richness rivaling our own cosmic neighborhood. Some theorists speculate that under the right conditions, dark matter might even form self-replicating patterns, a kind of dark life, operating on physics alien to everything we know. The evidence is tantalizing. Astronomers have found galaxies like Dragonfly 44, which has almost no visible stars yet weighs as much as the Milky Way. Its mass must be almost entirely dark matter, hinting at the possibility of entire universes hidden in plain sight. Even stranger are gravitational anomalies where patches of space seem to warp light more than expected, as if colossal dark matter structures are lurking just beyond our perception. But the real shocker: dark matter might not just be passive scaffolding. Some models suggest it could decay or annihilate, releasing energy that shapes galaxy formation. Others propose it interacts weakly with ordinary matter through a dark force we haven't discovered yet. If true, this would mean 2 parallel universes, ours and a shadow counterpart, constantly influencing each other in ways we're only beginning to guess. The hunt for answers is heating up. Deep underground, detectors like LUX Zeppelin wait for a stray dark matter particle to bump into an atom. In space, telescopes map gravitational distortions to trace the invisible architecture of the cosmos. And at the Large Hadron Collider, physicists slam particles together at near light speeds, hoping to create dark matter in the lab. What if we do find it? Unraveling dark matter's secrets could rewrite our understanding of gravity, revealing whether Einstein's theory needs an update or if entirely new physics is at play. It might even answer the ultimate question: are we alone in the universe, or is there a whole dark biosphere out there, utterly unrecognizable yet as real as the ground beneath our feet? The more we learn, the clearer it becomes: dark matter isn't just a missing piece of the puzzle. It could be the key to a reality far stranger than we ever dreamed. What if the universe isn't real, not in the philosophical sense, but literally a vast, intricate simulation running on some unfathomable computer? Elon Musk famously put the odds at 50-50, and he's not alone. From Silicon Valley to serious academic circles, the simulation hypothesis has gone from sci-fi trope to a legitimate question at the edge of physics. The reasoning is simple. if advanced civilizations could one day create simulations indistinguishable from reality, and if those simulations could spawn their own simulations, the number of artificial universes would dwarf the one real one. Statistically, we're probably in one of the copies, but how would we even know? Some scientists argue the answer might hide in the glitches, tiny imperfections in the fabric of reality that act like cosmic software bugs. Imagine playing a video game where the graphics are almost perfect, but if you look closely, you spot pixels or repeating textures. Now apply that to the universe. Researchers have scoured cosmic rays and high-energy particles for signs of pixelation, a telltale limit to how finely space-time can be divided. Others study whether fundamental constants, like the speed of light or the strength of gravity, might actually be adjustable parameters set by whatever or whoever booted up the simulation. Even quantum mechanics gets weirdly compatible with this idea. Take the observer effect, where particles don't settle on a state until measured. It's almost as if the universe is optimizing processing power, only rendering details when someone's looking. And entanglement, those instant connections between particles across vast distances, could be a clever programming shortcut, avoiding the need to calculate each particle's state individually. The implications are dizzying. If we're in a simulation, the laws of physics might not be fundamental truths but arbitrary rules coded into the system. Death could just be a log-out screen, the Big Bang, a server startup. Some theorists take it further, suggesting that if we ever discover the source code, we might even find ways to hack it, rewriting reality itself. Of course, not everyone's convinced. Critics argue the hypothesis is unfalsifiable, a clever thought experiment with no way to test it, but that hasn't stopped experiments. One team proposed firing high-energy particles at empty space to see if they hit an invisible resolution limit, like pixels on a screen. Others look for mathematical patterns in the cosmic microwave background that might reveal underlying code. Even if we never find proof, the simulation hypothesis does something remarkable. It forces us to question the nature of reality itself. Whether we're in a supercomputer or not, the idea reminds us how much we still don't understand and how wild the truth might turn out to be. After all, if this is a simulation, what's running it and what lies outside? The questions don't just challenge science. They blur the line between physics and metaphysics, leaving us wondering if the universe is a machine and if we're just lines in its program. White holes turn the terrifying logic of black holes inside out literally. While black holes suck everything in, never letting even light escape, white holes would do the exact opposite, violently spewing matter and energy outward like a cosmic fountain that nothing can enter. Imagine a black hole's event horizon, that point of no return but reversed, a boundary where matter can only exit, never enter. It's as if the universe has a one-way valve, and white holes are the exhaust pipe. These bizarre objects aren't just theoretical funhouse mirrors of black holes. They could solve some of the biggest mysteries in cosmology. Take gamma-ray bursts, those incomprehensibly powerful explosions that light up the distant universe for mere seconds, yet release more energy than the sun will in its entire lifetime. What could possibly fuel such violence? Some physicists speculate white holes might be the culprits, unleashing pent-up energy from another time or dimension in a catastrophic blast. Even wilder is the idea that the Big Bang itself could have been a white hole event, a singularity vomiting out the seeds of an entire universe. The math behind white holes isn't science fiction. Einstein's equations allow for their existence, and some interpretations of quantum gravity suggest black holes might eventually bounce into white holes over staggering timescales. Picture a black hole slowly evaporating via Hawking radiation until bang, the collapsed star at its core rebounds. not with a whimper but a universe-shaking eruption. Time dilation near the event horizon would mean that while this transformation might take billions of years from an outside perspective, inside the black hole's warped spacetime, it could happen in an instant. Yet the question remains, if white holes are possible, why haven't we seen one? One chilling answer is that they might only exist for a split second before collapsing back into black holes, making them cosmic mayflies here one moment and gone the next. Or perhaps they're hiding in plain sight. Some theorists propose that dark matter's gravitational effects could actually be the work of ancient white holes, their eruptions long since quieted but their mass still warping the cosmos. Others suggest white holes might exist in other universes, connected to black holes in ours through wormholes, creating a hidden network of cosmic plumbing. The implications are staggering. If white holes are real, they could rewrite the life cycle of stars, galaxies, and even the universe itself. A black hole's death might not be an eternal fade to darkness, but a transformation into something luminous and explosive. It challenges our understanding of entropy, suggesting that even the most extreme gravitational collapses might eventually reverse, like a cosmic phoenix rising from the ashes. But the most mind-bending possibility, white holes could be proof that the universe has a reset button, that what goes in must eventually come out somewhere, sometime. Whether they are lurking in distant galaxies disguised as dark matter or even birthed in particle colliders, one thing's certain: if we ever find one, it would force us to rethink not just how the universe ends, but how it begins again and again. We've been taught that the Big Bang was the ultimate beginning, a fiery explosion that birthed space, time, and everything we know. But what if it wasn't a start at all, just the latest turn in an endless cosmic cycle? Bouncing Cosmology flips the script, suggesting our universe is part of an infinite loop, expanding, contracting, and rebounding in a rhythm without beginning or end. Picture a cosmic heartbeat, each pulse a new Big Bang rising from the ashes of a previous collapse. This idea isn't just poetic, it solves some of the most stubborn puzzles in physics. The Big Bang singularity, where all known laws break down, has always been a glaring question mark. How can something come from nothing? A bouncing universe sidesteps this entirely. Instead of a mysterious creation event, imagine a prior cosmos reaching its limit, collapsing into an ultra-dense state, then springing back outward in a cosmic rebound. The Big Crunch becomes the Big Bang's precursor, like a phoenix dying only to be reborn. The math behind this is surprisingly elegant. Modified versions of Einstein's equations, combined with quantum gravity theories, show how a collapsing universe might not end in oblivion but hit a quantum bounce point. At unimaginable densities, quantum effects could counteract gravity's crush, triggering an expansion. Think of it like squeezing a rubber ball. Apply enough pressure, and it doesn't vanish, it snaps back. Some models even suggest these cycles could refine the universe each time, explaining why ours seems so finely tuned for life. Evidence might already be hiding in plain sight. The cosmic microwave background, the afterglow of the Big Bang, contains faint patterns that some scientists argue could be echoes of a pre-Big Bang universe. Certain anomalies in how galaxies cluster or how space stretches could be scars from a previous cycle. And if gravitational waves from the universe's earliest moments are ever detected with perfect precision, they might carry whispers of what came before. The implications are profound. An eternal cycle means time has no true start or finish, just an endless rhythm of creation and destruction. It redefines what we mean by the beginning, suggesting our universe is one chapter in an infinite saga. Civilizations might have risen and fallen in previous iterations, their stories erased by each collapse. The laws of physics themselves could evolve over cycles, with each rebound tweaking the constants that shape reality. But the most mind-bending possibility, if the cycle continues forever, then every configuration of matter and energy must eventually repeat. Somewhere in the vast tapestry of bouncing universes, there could be another you, another Earth, another everything, not just once, but an infinite number of times. It's a dizzying thought, but also a comforting one. Even if our universe meets its end, the story might never truly be over. At the heart of quantum mechanics lies one of the most baffling behaviors in physics: the way particles seem to change their nature depending on whether we're watching them or not. In the famous double-slit experiment, electrons act like waves when unobserved, creating interference patterns on a screen. But the moment scientists set up detectors to see which slit each electron passes through, they suddenly switch to behaving like discrete particles. It's as if the universe knows when we're looking and changes its rules accordingly. This isn't just a quirk of tiny particles, it hints at something far more profound: the possibility that consciousness itself plays an active role in shaping reality. The participatory universe theory takes this idea to its logical extreme. Pioneered by physicist John Archibald Wheeler, it suggests that reality doesn't fully exist until it's observed. Imagine a cosmic game of 20 questions where the answers aren't predetermined. The questions themselves bring the answers into being. In this view, the universe isn't a pre-written script but an ongoing creation, with every act of observation collapsing infinite quantum possibilities into a single, concrete outcome. Your attention, your awareness, might not just be witnessing reality, it could be stitching it together moment by moment. This concept turns traditional physics on its head. Instead of consciousness emerging from complex arrangements of matter, matter might emerge from consciousness. Think of it like a dream. While you're experiencing it, the world feels solid and real, but it's ultimately a construct of your mind. Could the waking universe operate on similar principles? Some interpretations of quantum mechanics, like the von Neumann-Wigner interpretation, take this literally, proposing that conscious observation is the only thing that resolves quantum uncertainty. But how could something as intangible as consciousness influence the physical world? One possibility lies in the nature of quantum superposition, the idea that particles exist in all possible states until measured. If consciousness acts as the measurement device, then the brain might not just process reality but participate in its creation. Experiments with delayed choice quantum erasers add fuel to this fire. They show that decisions made in the present can seemingly alter events that already happened in the past, as if time itself waits for conscious observation to finalize what's real. Critics argue this gives too much weight to human perception. After all, does a tree falling in the forest make sound if no one hears it? The participatory universe answer might be stranger. Until observed, the tree exists in a haze of possibilities, both fallen and standing, silent and loud. Only when a conscious mind engages does the event snap into focus. This doesn't mean we control reality with our thoughts, but that reality and observation are two sides of the same coin. The implications ripple across science and philosophy. If consciousness is fundamental, it could bridge the gap between quantum weirdness and our classical, everyday world. It might explain why the universe appears finely tuned for life, because life, through observation, is what tunes it. Some theorists even speculate about a universal consciousness, a vast, interconnected network of awareness weaving reality together at the quantum level. Whether this theory holds up to scrutiny or not, it forces us to confront a radical idea that the boundary between the observer and the observed might be far thinner than we ever imagined. The next time you look at the stars, consider this: your gaze might not just be taking in the cosmos, but in some small way helping to create it. negative mass sounds like something ripped straight from a physicist's wildest dreams, matter that doesn't just resist gravity but actively pushes against it. Picture a substance that, when dropped, falls upward instead of down, or a planet made of this bizarre material that repels everything around it like a cosmic magnet flipped the wrong way. This isn't just theoretical whimsy. If negative mass exists, it could unlock technologies straight out of science fiction, from warp drives bending space-time to traversable wormholes stitching the universe together like shortcuts through folded paper. The math behind this strange idea isn't as far-fetched as it seems. Einstein's equations allow for negative mass solutions, and certain quantum field theories hint at exotic particles that could exhibit these properties. The implications are staggering. Normal mass warps space-time inward, creating the gravity wells that keep planets in orbit and light bending around black holes. Negative mass would do the opposite, stretching space-time outward like a hill instead of a valley. Place enough of it near positive mass, and you could theoretically engineer a warp bubble, compressing space in front of a spacecraft while expanding it behind, allowing faster-than-light travel without breaking relativity's speed limit. But the real magic happens when you combine negative and positive mass. Imagine threading a wormhole, a tunnel through space-time, with negative mass to keep it stable. Ordinarily, wormholes snap shut instantly under their own gravity, but negative mass could act as cosmic scaffolding, propping the throat open long enough to step through. Some models even suggest that advanced civilizations might already be using such shortcuts, weaving a hidden subway system across the cosmos. Energy wouldn't just bend to negative mass's rules, it would flip them entirely. Normally, pushing an object forward requires expelling energy backward, like a rocket firing exhaust. Negative mass could defy this, accelerating in the direction it's pushed without the usual energy penalty. A spacecraft equipped with it might surf anti-gravity waves like a sailboat catching the wind, needing no fuel beyond the strange matter itself. The catch: no one's ever detected negative mass, and creating it in a lab would require manipulating quantum fields in ways we barely understand. Yet tantalizing clues linger. Dark energy, the mysterious force accelerating the universe's expansion, behaves eerily like a negative mass effect on cosmic scales. Some theorists speculate it might literally be negative mass thinly spread across the vacuum of space. Even more provocative is the Casimir effect, where quantum fluctuations create regions of negative energy density, offering a microscopic glimpse of how repulsive gravity might operate. If we ever harness this phenomenon, the revolution wouldn't just be technological, it would be philosophical. Negative mass challenges our most basic assumptions about cause and effect, energy conservation, and the very fabric of reality. A universe where matter can push as easily as pull isn't just stranger than we imagine. It might be stranger than we can imagine. And that's the most thrilling possibility of all, because somewhere in those uncharted laws of physics, the future of exploration could be waiting. The cosmos should be teeming with life, with billions of galaxies, each hosting billions of stars and planets. The numbers scream that we can't possibly be alone. Yet when we listen, the universe echoes back with silence, an eerie absence of signals, probes, or visitors. This is the Fermi Paradox, the glaring contradiction between the high probability of alien civilizations and the complete lack of evidence for them. One chilling explanation, the dark forest theory. Imagine the universe as a vast, shadowy woodland where every civilization is a hunter hiding among the trees. Making noise, sending signals, announcing your presence, could invite destruction from predators far more advanced. Staying silent isn't just cautious, it's survival. This isn't paranoia, it's game theory applied to cosmic scales. any civilization that reveals itself risks attracting the attention of others who might see it as a threat or resource. The safest strategy is to stay hidden, observe quietly, and strike first if necessary. It's a universe where trust is impossible because the stakes are annihilation. Even if most civilizations are peaceful, it only takes one aggressive actor to turn the cosmos into a battlefield, those flashing lights in the night sky. Not friendly neighbors, potential snipers, but the dark forest isn't the only answer. Some scientists propose we're living in a cosmic zoo, where advanced civilizations observe us from a distance like wildlife in a preserve. They might have ethical guidelines against interfering, or perhaps they're waiting for us to reach a certain technological maturity before making contact. It's the galactic equivalent of a prime directive, a policy of non-interference until we're ready. Then there's the simulation angle. If our universe is an artificial construct, the absence of aliens might be a design choice. Maybe we're alone because we're the focus of the simulation, or extraterrestrials simply weren't programmed into the scenario. It's a twist on the Fermi Paradox that doesn't require sinister explanations, just lines of code. Another possibility is even more humbling. We might be early. The universe is 13.8 billion years old, but it could endure for trillions more. If intelligent life tends to emerge later in cosmic history, we might be among the first pioneers in an infant universe. The implications are staggering. If the dark forest is real, humanity's efforts to broadcast our presence from radio signals to Voyager's golden records could be catastrophically naive. Conversely, if we're in a zoo or simulation, our search for meaning takes on new dimensions. Either way, the silence of the cosmos isn't just a puzzle. It's a mirror, reflecting our deepest fears and hopes about what's really out there. And until we know for sure, every signal we send is a gamble with stakes we can't even calculate. Time crystals sound like something straight out of a wizard's playbook, structures that don't just exist in space, but actively dance through time. Unlike ordinary crystals, where atoms arrange in repeating patterns like a grid of tiles, time crystals flip the script. Their structure repeats at regular intervals in time, like a snowflake that reforms itself over and over without melting. This isn't just a curious thought experiment, it's a real quantum phenomenon that Nobel laureate Frank Wilczek first proposed, and it defies one of the most fundamental laws of nature, entropy. Entropy dictates that everything in the universe tends toward disorder. Ice melts, buildings crumble, stars burn out, but time crystals laugh in the face of this cosmic trend. They're the closest thing to perpetual motion we've ever discovered, oscillating between states indefinitely without any energy input. Imagine a clock that ticks forever without winding, or a pendulum that swings eternally without friction slowing it down. That's the magic of time crystals. They're not just stable, they're eternally cycling, locked in a rhythm that even the universe's march toward chaos can't disrupt. How is this possible? The secret lies in quantum entanglement, that spooky connection where particles influence each other instantly across vast distances. In a time crystal, entangled particles sync up in a delicate dance, flipping their quantum states back and forth like a metronome set to the universe's heartbeat. Even more bizarre, these oscillations don't match the frequency of whatever force kicks them off, like a guitar string vibrating at a different pitch than the one you plucked. It's as if time crystals have their own internal tempo, a rhythm written into the fabric of quantum reality itself. Scientists have already created these exotic states in labs, using chains of ions or diamonds with imperfections to mimic the behavior. But the implications stretch far beyond a laboratory curiosity. Time crystals could revolutionize quantum computing, acting as near-perfect memory storage that doesn't degrade over time. In a field where quantum qubits are notoriously fragile, a system that resists entropy could be the missing piece to unlock unprecedented processing power. Some theorists even speculate that time crystals might help us simulate complex quantum systems, like high-temperature superconductors or the behavior of distant stars with uncanny accuracy. But the most tantalizing possibility, time crystals might rewrite our understanding of time itself. If matter can have a built-in rhythm independent of external forces, what does that say about the nature of time as we perceive it? Could time crystals hint at deeper layers of reality where time isn't a smooth flow but a series of quantum ticks, like frames in a cosmic film strip? The wildest part, time crystals aren't just a theoretical curiosity, they're a doorway to technologies that seem like magic, to answers about the universe's deepest mysteries, and perhaps even to a new kind of physics where the arrow of time isn't just something we observe, but something we might one day control. What if consciousness isn't something that emerges from complex brains, but is instead woven into the very fabric of reality? Panpsychism, one of the oldest and most radical ideas in philosophy, suggests exactly that every particle, every star, every galaxy might possess some form of inner experience. Not in the way humans think or feel, but as a fundamental property of matter itself, like mass or charge. Imagine the universe not as a cold, mechanical clockwork, but as a vast, shimmering network of awareness, where even an electron might have a whisper of subjective experience. This isn't fantasy, it's a serious attempt to solve the hard problem of consciousness, why and how physical processes in the brain give rise to rich inner lives. The implications are staggering. If panpsychism is true, then consciousness didn't evolve. It was always there, waiting to be organized into more complex forms. Think of it like temperature. A single molecule doesn't have a temperature, but trillions jostling together create heat. Similarly, simple particles might have rudimentary experience, but when arranged into systems as intricate as human brains, they give rise to self-reflection, emotion, and wonder. This flips traditional materialism on its head. Instead of consciousness being an accidental byproduct of neurons firing, it becomes a basic feature of the cosmos, as intrinsic as space-time. Critics argue this is mysticism dressed up as science. How could a rock or a star experience anything? But panpsychists counter with a compelling question. How does unconscious matter suddenly become conscious when arranged in the right way? There's no known law of physics that explains the leap from electrochemical signals to the taste of coffee or the ache of nostalgia. Panpsychism offers an elegant solution. The seeds of consciousness were there all along. Some theories go even further. Integrated information theory, for example, proposes that consciousness arises whenever information is processed in a unified way, meaning not just brains, but even sophisticated networks like computers or ecosystems might possess some degree of awareness. Picture the internet as a fledgling global mind, or Earth's biosphere as a slow, planetary-scale thinker. Even black holes, those cosmic vacuum cleaners, might process information in ways that hint at a bizarre form of cosmic sentience. The most mind-bending possibility: if the universe itself is conscious, then our individual minds might be like neurons in a vast cosmic brain. The thoughts we think, the art we create, the science we discover, could they be fragments of a greater awareness unfolding? It's a humbling thought, but also a strangely beautiful one. Instead of being lonely accidents in an indifferent void, we might be participants in a grand, self-aware cosmos, discovering itself through our eyes. Whether panpsychism holds up to scrutiny or not, it forces us to confront a profound mystery, the nature of our own awareness. And in doing so, it blurs the line between science and spirituality, between the observer and the observed. The next time you gaze at the night sky, consider this: you might not just be looking at the universe, you might be the universe looking back at itself. Quantum Darwinism flips our understanding of reality on its head by asking a deceptively simple question: why does the world seem solid and predictable when quantum mechanics tells us it should be a blur of infinite possibilities? The answer might lie in a process eerily similar to natural selection, where only the most fit quantum states survive the chaos to become the reality we perceive. Imagine a quantum version of survival of the fittest, where particles aren't just collapsing into definite states upon observation, they're competing to be the ones we notice, like a cosmic game of last man standing. At the heart of this idea is the quantum phenomenon of decoherence, where fragile superpositions, those ghostly states where particles exist in multiple places at once, get battered by their environment until only the most stable configurations remain. Think of it like 1,000 radio stations playing at once, but only the strongest signal breaks through the static. In this case, the signal is the quantum state robust enough to withstand constant interactions with other particles, while the others fade into noise. These survivors become what we call objective reality, the world we all agree exists because it's the one that's been repeatedly selected by the environment. This isn't just abstract theorizing. Quantum Darwinism explains why we don't see Schrödinger's cats alive and dead in our daily lives. The states we perceive are the ones that have been copied and broadcast across countless particles, like a meme spreading so widely it becomes undeniable. Your coffee cup stays on the table, not in some quantum limbo, because its position has been redundantly imprinted on photons, air molecules, and even the atoms in your eyes, a consensus forged by relentless environmental interaction. It's as if reality itself evolves, with only the most communicable states passing the test of time. The implications ripple far beyond quantum physics. If our perception of the world is shaped by a Darwinian process at the subatomic level, it suggests that objectivity itself might be an illusion, a temporary truce among quantum possibilities. Even more provocative is the idea that consciousness might play a role in this selection. While quantum Darwinism doesn't require an observer to collapse reality, it raises the possibility that our attention acts as a filter, amplifying certain states while others fade into oblivion. Critics argue this is just a fancy restating of decoherence theory, but supporters counter that it provides something deeper, a mechanism for how classical reality emerges from quantum weirdness without resorting to mysterious collapses or parallel universes. It's a bridge between the microscopic and macroscopic worlds, showing how complexity and stability arise from chaos. The most mind-bending part, quantum Darwinism hints that reality isn't just out there waiting to be discovered. It's shaped by an invisible process of selection, where what we perceive is only the tip of a vast, churning quantum iceberg. The next time you glance at a tree or touch a doorknob, remember, you're not just observing the world, you're witnessing the winners of a billion-year-old competition, the quantum states that fought their way into existence. Time is the invisible thread stitching our reality together, the reason yesterday feels different from tomorrow, why a cup shatters when dropped, and why we remember the past but not the future. But what if, at the deepest levels of existence, time doesn't exist at all? Some of the most cutting-edge theories in quantum gravity suggest exactly that. Time might vanish when we zoom in close enough, leaving behind a frozen, timeless web of relationships where before and after lose all meaning. Picture the universe as a vast, intricate tapestry. From a distance, it tells a story with a clear sequence, threads weaving forward in a pattern we call time. But up close, the threads don't move. They simply are, locked in an eternal arrangement where every connection exists simultaneously. This is the world without time, a place where cause and effect aren't steps in a chain but fixed points in an unchanging structure. The Big Bang isn't an explosion in the past, it's just another knot in the cosmic weave, as present as the device you're holding right now. The implications shatter our most basic assumptions. Physics relies on time to define motion, energy, even entropy, the arrow that separates past from future. Without it, equations describing reality must be rewritten from the ground up. Some theories, like loop quantum gravity, replace time with relationships between events, like a cosmic version of Friends on a social network, where now is just whichever post you're currently viewing. Others, like the Wheeler-DeWitt equation, describe a universe frozen in an eternal instant, where change is an illusion emerging from our limited perspective. But here's the real mind bender. If time isn't fundamental, how do we explain the undeniable flow of experience? Why does life feel like a movie playing frame by frame instead of a completed painting? One radical answer is that consciousness itself might stitch moments together, creating the illusion of sequence from timeless raw material. Think of flipping through a flipbook. The animation only exists because your brain connects the still images. Without a viewer, there's just a stack of paper. Experiments are already probing this idea. Quantum systems show hints of timeless behavior, with particles making decisions that seem to ignore the usual rules of cause and effect. Even black holes, those cosmic clocks where time grinds to a halt at the event horizon, might be windows into a deeper, timeless reality, the most unsettling possibility. If time isn't real, then free will, the sense that our choices shape the future, might be a beautiful fiction. Yet it's also liberating. In a timeless universe, every moment exists forever, preserved like a butterfly in amber. The first kiss, the last goodbye, the discoveries yet to come, they are all out there, not lost to the past or hidden in the future, but eternally present in the frozen architecture of reality. It's a vision that doesn't just challenge physics, it redefines what it means to exist. What if every electron you've ever encountered in the screen you're staring at, in the air around you, even inside your own body, wasn't a separate particle at all, but the same single electron, weaving through time like a cosmic thread stitching reality together? This is the jaw-dropping premise of the One-Electron Universe, a theory so bold it was first proposed by physicist John Wheeler as a playful thought experiment, until the math started to suggest it might actually be possible. Imagine a solitary electron, not just moving forward in time like we're used to, but oscillating endlessly between the birth of the cosmos and its eventual end. Each backward trip would look to us like a positron, the electron's antimatter twin, meaning every positron we observe could just be that one electron traveling in reverse. At first glance, this seems impossible. After all, we detect electrons everywhere simultaneously in lab experiments, starlight, even deep underground. But quantum mechanics has a way of bending logic. Particles pop in and out of existence constantly, and antimatter is mathematically equivalent to matter moving backward through time. Wheeler realized that if you could track a single electron's path across all of time, its zigzagging trajectory might crisscross the present moment countless times, creating the illusion of a universe teeming with electrons. It's like watching a dancer under a strobe light. What appears to be a crowd might just be one performer, glimpsed at different moments. The implications are staggering. If true, this would mean all electrons, every single one in every atom of every galaxy, are fundamentally the same entity. The carbon in your DNA, the iron in Earth's core, the silicon in distant exoplanets, all linked by this single, timeless particle. It's a radical form of unity hidden beneath the surface of reality's diversity. Some interpretations even suggest this could extend to other particles, hinting that all matter might be echoes of a handful of primordial threads vibrating through dimensions we can't perceive. But how could science ever test such an outlandish idea? Surprisingly, there are clues. If every electron is truly identical, their properties, mass, charge, spin, should be indistinguishable beyond measurement error. And so far, they are. No experiment has ever found a single electron that differs from another. Even more intriguingly, the One-Electron Universe elegantly explains why electrons and positrons always appear in perfect pairs during particle collisions. They're not being created, just momentarily revealed as the solitary electron changes its temporal direction. Critics argue this is a beautiful but untestable metaphor, a poetic way to interpret quantum equations rather than a physical reality. Yet supporters point to deeper mysteries it might solve, like why the universe has so much more matter than antimatter. If antimatter is just matter traveling backward, the asymmetry could hint at a fundamental arrow of time woven into the cosmos, the most profound implication. If Wheeler was right, the boundary between past, present, and future isn't just blurry, it might not exist at all. That electron dancing through time could be touching the first stars, your retinas right now, and civilizations a trillion years hence, all equally real in a universe where time is less a river and more a hall of mirrors. It's a vision that doesn't just unite matter, it dissolves the illusion of separation altogether. Black holes are the ultimate cosmic vaults, swallowing stars, light, and anything else that strays too close, locking it away behind an event horizon from which nothing is supposed to escape. But here's the problem. Quantum mechanics insists that information can never be truly destroyed. Every particle, every interaction, leaves an indelible mark on the universe. So what happens when these two unstoppable forces collide? That's the black hole information paradox, a puzzle so profound that solving it could rewrite our understanding of reality itself. Stephen Hawking first ignited this debate when he realized black holes aren't entirely black. They slowly leak energy, now known as Hawking radiation, fading away over eons. But here's the catch. This radiation appears random, carrying no trace of the information swallowed by the black hole. It's like burning a library and claiming the smoke particles contain the patterns of every book. If the information is truly lost, quantum mechanics breaks. The universe would have a cosmic delete button, erasing the very history that makes physics predictable. Desperate for solutions, physicists have proposed mind-bending escapes. One possibility: the information isn't lost, it's encoded in the Hawking radiation itself, scrambled like a quantum cryptogram. Decode it, and you could reconstruct the original star or spaceship that fell in, pixel by pixel. It's as if black holes aren't destroyers but shredders, chopping information into pieces so tiny we've yet to recognize the pattern. Then there's the wormhole gambit. Some theories suggest black holes might connect to white holes through hidden tunnels in space-time, ejecting information into other universes or distant corners of our own. Imagine a letter dropped into a mailbox that reappears intact in another galaxy. The information isn't destroyed, just relocated in a way that keeps quantum mechanics intact. But the wildest idea, holography. If the universe is a projection, as the holographic principle suggests, then black holes might store information as patterns on their surfaces, like a cosmic DVD. What we perceive as destruction is just data being rewritten in a dimension we can't see. The stakes couldn't be higher. If information can vanish, the entire framework of quantum theory, the foundation of everything from chemistry to computing, crumbles. But if it's preserved, even in the belly of a black hole, it hints at a universe where every event, no matter how catastrophic, is eternally recorded. The answer might lie in experiments mimicking black holes with ultra-cold atoms or detecting subtle quantum echoes in space. Either way, this paradox isn't just about black holes. It's about whether the universe forgets or remembers everything forever, and that changes how we see existence itself. Imagine waking up one day with all your memories intact, your childhood, your job, even watching this video only to realize none of it is real. You're not a person but a momentary flicker of consciousness, conjured into existence by pure random chance in the vast, empty void of space. This isn't a nightmare. It's the Boltzmann brain paradox, one of the most unsettling ideas in physics. According to this theory, in an infinite universe governed by entropy, random quantum fluctuations could spontaneously assemble a fully self-aware mind, complete with fabricated memories and a hallucinated reality. And statistically, in an eternal cosmos, these phantom observers might outnumber real, biological beings like us by an unimaginable margin. The paradox takes its name from Ludwig Boltzmann, the 19th century physicist who revolutionized our understanding of entropy. He showed that disorder tends to increase over time, but also that tiny, temporary reversals are possible. Stir a drop of ink into water, and it spreads evenly, but given enough time, random molecular motion could, by sheer luck, reconcentrate the ink into a droplet for a split second. Now scale that up to the universe. Given infinite time, even the most improbable events become inevitable, including the random assembly of a functioning brain with a complete but false perception of reality. Here's where it gets spine-chilling. If the universe lasts forever, Boltzmann brains should dominate the cosmos. Think of flipping a coin forever. Eventually, you'll get a sequence of 1,000 heads in a row. Similarly, over eternity, the void could churn out countless self-aware illusions for every real, evolved consciousness. So how do we know we're not one of them? Your sense of continuity, your memories, even the device in your hands, all could be a fleeting mirage, vanishing as suddenly as it appeared. Physicists recoil from this idea not because it's spooky, but because it undermines science itself. If most observers are Boltzmann brains, then our perception of an orderly, consistent universe might be a statistical fluke, not evidence of actual laws. It's like a hallucination where you remember conducting experiments that never happened, confirming physics that don't exist. Some cosmologists argue this paradox actually disproves eternal universes or certain multiverse theories, because if they were true, we shouldn't be here having this conversation. We should be Boltzmann hallucinations, yet the paradox lingers, forcing us to confront the fragility of reality. Maybe the only way out is to accept that consciousness, not matter, might be the bedrock of existence. Or perhaps the universe has a built-in expiration date, cutting off the infinite time needed for Boltzmann brains to dominate. Either way, this isn't just a thought experiment. It's a mirror held up to our deepest assumptions about what's real and how we know it. The next time you question a memory or déjà vu, consider this. The universe might be whispering that nothing is as solid as it seems. Mathematics has always been the language of physics, the secret code scribbled in nature's margins. But what if it's more than just a tool? What if numbers and equations aren't describing reality, but our reality? This is the radical heart of Max Tegmark's mathematical universe hypothesis, a theory so audacious it claims the cosmos isn't just governed by math, it is math. Every particle, every force, even the flicker of your thoughts, might not be made of matter or energy, but of pure mathematical structure. Imagine the universe as an infinite equation solving itself, where the stars are variables, gravity is a function, and consciousness is an emergent property of some deeper calculation. This isn't just abstract philosophizing. Tegmark's argument starts with a simple observation. the uncanny effectiveness of mathematics in explaining the universe. From the spiral of galaxies to the orbits of electrons, nature follows mathematical blueprints with eerie precision. Even phenomena we once thought were chaotic, like weather or brain activity, reveal hidden mathematical order when examined closely. The leap Tegmark makes is to ask why stop at saying math describes reality. What if reality is math? In this view, the universe isn't a physical thing running on mathematical rules. It's a mathematical object that we're interpreting as physical. Think of it like a video game. The world you see on screen feels solid, but underneath, it's all code. Tegmark suggests our universe might be the same, an illusion woven by numbers. Critics argue this reduces existence to a sterile abstraction, stripping away the richness of experience. But Tegmark counters that math isn't cold, it's infinitely expressive. A single equation can describe the curve of a rose petal or the swirl of a galaxy. Consciousness, in this framework, might arise from complex computational structures, like self-referential loops in a cosmic algorithm. It's not that you're just math, it's that math can be everything. The implications are staggering. If the universe is fundamentally mathematical, then all possible mathematical structures exist somewhere, meaning every conceivable cosmos, every alternate physics, is as real as our own. Somewhere, a universe might run on geometry we can't visualize, with forces that have no analog here. Even more provocative, if consciousness is mathematical, then artificial minds could be as real as biological ones, and digital beings might ponder their own equations in some vast computational space. The theory also redefines the search for a theory of everything. Instead of hunting for the particles or forces that make up reality, physicists might look for the ultimate equation from which all others derive. Some versions of string theory already hint at this, suggesting that the universe's diversity emerges from a single mathematical symmetry. But how could we ever test such an idea? Tegmark points to the frontiers of quantum gravity, where space-time itself might dissolve into pure information, a network of logical relationships waiting to be decoded. If experiments reveal that reality has a digital or computational foundation, it would lend weight to the mathematical universe. Even consciousness research could play a role. If we ever build a machine that claims to be aware and its inner workings are purely mathematical, that might suggest subjectivity itself is an equation. Whether Tegmark's hypothesis holds or not, it forces us to confront a profound question. Is the universe something we discover or something we invent? If math is the ultimate reality, then the line between the physicist and the poet blurs. Both are uncovering verses in an endless cosmic poem, written in a language older than time. And that poem might contain stanzas we haven't even dreamed of yet. The great filter looms over humanity like a cosmic checkpoint, an invisible barrier so formidable that it explains why, despite billions of habitable planets, the universe remains eerily silent. The idea is simple yet terrifying. Somewhere between the spark of life and the conquest of the stars, there's a wall, a catastrophic challenge so overwhelming that almost no civilization survives it. The real question isn't just what the great filter is, it's where it lies, and the answer could mean we're either the rarest success story in the cosmos or doomed to vanish before we ever leave our cradle. Consider the possibilities. If the filter is behind us, something we've already survived, then we might be among the first to beat the odds. Maybe the jump from simple chemistry to self-replicating life is astronomically unlikely. Or perhaps intelligent civilizations routinely wipe themselves out with nuclear war or runaway AI. In this scenario, Earth is a miracle, and humanity's survival is a fluke so rare that the galaxy remains empty. But if the filter is ahead of us, lurking in the uncharted territory between our current technology and interstellar expansion, then every rocket we launch, every AI we build, every energy source we unlock could be bringing us closer to collapse. The evidence is unsettling. On one hand, life appeared on Earth almost as soon as the planet cooled, suggesting simple biology might not be the filter. But complex tool using intelligence took billions of years, and we've yet to find another example. Even more troubling, every civilization we know of, ours included, has developed the means to destroy itself long before mastering space travel. The same tools that could build starships also build bombs. The same curiosity that drives exploration could accidentally unleash a planet-killing pathogen or an unstoppable machine intelligence. Yet there's a third, darker option. The filter isn't a single event but a gauntlet. Maybe civilizations must survive not just one existential threat, but dozens: climate collapse, asteroid impacts, gamma-ray bursts, societal collapse, each winnowing the field until only a handful remain. If true, then every day we endure is a statistical anomaly, a temporary reprieve before the next trial. The stakes couldn't be higher. If the filter is past us, we might be destined to inherit the stars. If it's ahead, our best hope might be to slow down, to tread carefully, to prioritize survival over reckless advancement. Because in a silent universe, the only thing scarier than being alone is realizing why everyone else is gone. The universe as we know it won't just fade, it might be ripped apart from within. Dark energy, that mysterious force accelerating the expansion of space, could be setting the stage for the most desolate fate imaginable, the Big Rip. Picture a future so distant it defies comprehension, where the very fabric of reality unravels. Galaxies, stars, even atoms would be torn asunder, not by an explosion, but by the silent, unstoppable stretching of space itself. This isn't just an end, it's an erasure, leaving behind a phantom universe of isolated particles drifting eternally in an ever-expanding void. The math behind this apocalypse is eerily straightforward. If dark energy's strength increases over time, a possibility some observations hint at its grip on spacetime would intensify. First, galaxy clusters would be pulled apart, their gravitational bonds overcome like tissue paper in a hurricane. Billions of years later, individual galaxies would disintegrate, stars flung into the darkness like embers from a dying fire. Then, as the expansion grows exponentially, even solar systems would be shredded. Planets torn from their suns, moons from their planets, until finally, in the last agonizing moments, atoms themselves would be stretched beyond their limits. Protons and electrons, the building blocks of matter, ripped apart as spacetime's expansion overcomes the very forces holding them together. What remains would be a graveyard of fundamental particles, each alone in an infinite void, unable to interact with anything else. No light, no heat, no structure, just a cold, featureless expanse where the concept of distance loses all meaning. Even time, stripped of events to mark its passage, might as well cease to exist. It's a fate more desolate than heat death, more final than a black hole's singularity. At least in those scenarios, something remains. The Big Rip leaves behind nothing but echoes of a universe that once was. Yet the most unsettling part isn't the destruction, it's the timing. If dark energy behaves as some models predict, this could happen in as little as 22 billion years. A blink of an eye on cosmic scales, the Milky Way and Andromeda might still be merging when the first cracks in reality begin to show. Civilizations that rise in the far future could witness the sky tearing itself apart, their last moments spent watching the stars vanish one by one as the cosmos disintegrates around them. But there's a twist. This nightmare scenario hinges on dark energy's still unknown nature. If its strength plateaus or fades, the universe might avoid the rip, meeting a slower, colder end. That's why scientists are racing to measure dark energy's behavior with unprecedented precision. Telescopes like the Vera Rubin Observatory and the Euclid spacecraft are mapping the cosmos's expansion in exquisite detail, hunting for clues that could confirm or condemn our universe to this phantom fate. The Big Rip forces us to confront a profound question. Does the universe owe us permanence? We're accustomed to thinking in terms of billions of years, but eternity is a different beast entirely. In a cosmos where even atoms aren't safe, the only certainty is that nothing lasts forever, not the stars, not the laws of physics, and certainly not us. Yet there's a strange beauty in that impermanence. It means every moment, every connection, every discovery is a fleeting spark in the darkness, and perhaps that's enough. What if death isn't an end, but a doorway, one that leads not to oblivion, but to another version of reality? The quantum afterlife theory takes the strangest aspects of quantum mechanics and applies them to the most personal mystery of all: what happens when we die? At its core, this idea suggests that consciousness isn't just a byproduct of brain chemistry, but something far deeper, a quantum phenomenon that doesn't vanish when the body fails, but instead branches into parallel worlds, continuing its journey in another timeline. It's a concept that blurs the line between cutting-edge physics and ancient spiritual beliefs, offering a vision of immortality written not in scripture, but in the mathematics of the multiverse. The foundation of this idea lies in quantum superposition, the principle that particles can exist in multiple states at once until observed. In the many worlds interpretation, every quantum decision spawns new universes, each hosting a different outcome. Now apply that to consciousness. When you face a life-threatening situation, a car crash, a terminal illness, quantum mechanics suggests there's always a universe where you survive, no matter how slim the odds. From your perspective, you'd never experience death, only an unbroken chain of existence where you always land in the timeline that continues. It's as if reality itself conspires to keep you perceiving, no matter how many branches fade away behind you. This isn't just speculative philosophy. Some scientists argue that the brain might harness quantum processes, particularly in structures like microtubules within neurons. If true, then consciousness could be more than just electrical signals. It might be a quantum computer, its calculations spreading across realities. When death occurs in one world, the quantum information of your awareness simply shifts to another, like a radio tuning to a different frequency. You wouldn't notice the transition any more than you notice the split-second gap between frames in a movie. The implications are staggering. Near-death experiences, those vivid reports of tunnels of light or past memories, might not be hallucinations, but glimpses of consciousness transitioning between branches. Children who claim to remember past lives could be tapping into memories from parallel selves in other timelines. Even déjà vu might be more than a glitch. It could be a fleeting resonance with another version of you living a slightly different moment. Critics argue this is wishful thinking dressed up in quantum jargon. After all, if consciousness branches endlessly, why don't we remember other lives? Why does death feel so final to those left behind? Supporters counter that memory is tied to the brain. Each new branch would carry only the memories of its own timeline, leaving other versions as faint echoes at best. And for those mourning a loved one, the comfort is cold. Somewhere, their person lives on, but not here. Yet the quantum afterlife does something remarkable. It merges the cold equations of physics with the warmth of human hope. Whether it's testable remains an open question, but it forces us to confront a profound possibility, that death might not be a full stop, but a comma in the story of consciousness. And in a multiverse where every possibility plays out, perhaps the most astonishing thing isn't that we survive, but that we ever thought we could disappear at all. Reach out and touch the screen in front of you. It feels solid, unyielding, real. But here's the cosmic joke: you're not actually touching anything at all. Every atom in your hand is hovering nanometers above the atoms in the screen, held at bay by electromagnetic forces, and those atoms themselves, they're almost entirely empty space. If you could shrink down to the size of an atomic nucleus, a single grape in a football stadium, the nearest electron would be a speck of dust orbiting somewhere in the nosebleed seats. The rest nothing, a void so vast that if you removed all the empty space from every human on Earth, the entire population would fit inside a sugar cube with room to spare. So why doesn't the world feel like a ghostly hologram? Why do stairs hold your weight or baseballs smack into gloves with a satisfying thud? The answer lies in the invisible scaffolding of reality, quantum fields. These aren't just abstract ideas, they're pulsating, omnipresent layers of energy that fill every inch of the so-called empty space. When you push against a wall, it's not the solid nuclei repelling you. It's the interaction between the electron clouds surrounding those nuclei, their quantum fields bristling like angry cats. The electromagnetic force carried by photons creates the illusion of solidity by making those fields stiffen when compressed. It's less like two objects colliding and more like two powerful magnets resisting each other, an invisible force field doing all the heavy lifting. But the weirdness goes deeper. Quantum fields don't just explain solidity, they rewrite what emptiness even means. A perfect vacuum, the kind you'd imagine as true nothingness, doesn't exist. Even in the deepest voids of space, quantum fields vibrate with potential, constantly spawning pairs of virtual particles that wink in and out of existence. This quantum foam means emptiness is teeming with activity, a seething underworld where particles borrow energy from the future to exist for fleeting instants. The chair you're sitting on, it's not just atoms, it's a storm of transient particles and fields holding it together, a temporary consensus in the chaos. This raises a haunting question. If matter is mostly void and solidity is just a stubborn illusion maintained by forces we can't see, what else are we wrong about? The hardness of steel, the warmth of sunlight, even the beating of your heart, all of it emerges from interactions between invisible fields and particles that barely occupy any space at all. Reality isn't just stranger than we imagine, it's stranger than we can imagine, a magician's trick performed on a scale so small, our senses never stood a chance. The next time you stub your toe, remember, the pain is real, but the thing you kicked, it's closer to a whisper of energy than a solid object, a cosmic sleight of hand we're only beginning to understand. We measure the universe's age at 13.8 billion years, the time since the Big Bang sent matter and energy rushing outward in a fiery explosion. But what if that moment wasn't the true beginning? What if it was just a chapter in an infinitely old cosmic story, with time stretching backward into an unfathomable past? This is the radical possibility that challenges one of cosmology's most fundamental assumptions, that the universe had a definitive starting point. Some theories suggest our observable cosmos is just a local bubble in an eternal, ageless expanse where the Big Bang wasn't creation but a transition. Think of it like a pond frozen on a winter's day. The ice forms suddenly, cracking and expanding across the surface, but the water beneath has existed long before the freeze. Similarly, the Big Bang could mark the moment our pocket of reality crystallized out of something far older and more mysterious, a cyclic universe where expansion and contraction play out endlessly, or a multiverse where new regions constantly inflate like bubbles in an infinite ocean. The math behind this is more than speculative. Certain models of loop quantum gravity, a leading candidate for unifying quantum mechanics and general relativity, eliminate the singularity at the Big Bang entirely, replacing it with a bounce from a previous collapsing phase. Time, in this view, doesn't begin, it rewinds. The evidence might already be hiding in plain sight. The cosmic microwave background, that faint glow from the early universe, contains anomalies, cold spots, and uneven patterns that some scientists argue could be bruises from collisions with other universes in a pre-Big Bang era. Even dark flow, the mysterious motion of galaxy clusters in a preferred direction, might hint at gravitational tugs from structures beyond our observable horizon, remnants of an older cosmos. But the implications go deeper than cosmology. An infinitely old universe reshapes our understanding of cause and effect. If time has no true starting point, then every event is both an end and a beginning, a link in an endless chain. The laws of physics themselves might evolve over eons, with constants like the speed of light or the strength of gravity slowly shifting across eternity. Life could arise, die out, and arise again in cycles so vast they dwarf the lifetime of stars. The most mind-bending possibility: if the universe has always existed, then somewhere in the abyss of time, every configuration of matter and energy must have occurred not once but an infinite number of times. There could have been civilizations that rose to godlike mastery over physics, only to vanish into the dark, their stories erased by time. The atoms in your body might have been part of countless other lives, other worlds before assembling into you. It's a vision that doesn't just extend the past, it obliterates the very idea of a first moment, leaving us floating in an ocean without shores. Yet for all its grandeur, this idea forces a humbling question: how would we ever know? If the pre-Bang universe left no detectable traces, or if its physics operated under entirely different rules, we might be forever trapped in our 13.8 billion-year bubble, guessing at the infinite beyond. But that's the thrill of cosmology. The universe's greatest mysteries might not lie ahead, but behind us, in a past so deep it has no bottom. Gravity feels like the most fundamental force in the universe, the invisible hand that shapes galaxies, pins us to the planet, and guides planets in their orbits. But what if it's all an illusion, not in the sense that gravity doesn't exist, but that it might not be a fundamental force at all? Enter entropic gravity, a radical theory that reimagines gravity as a side effect of something far deeper: the universe's relentless drive toward disorder. Imagine gravity not as a force transmitted by particles or warps in spacetime, but as a statistical mirage, a cosmic consequence of quantum information scrambling to maximize entropy, like heat dissipating from a cup of coffee. This idea turns conventional physics on its head. Instead of gravity being woven into the fabric of reality from the beginning, entropic gravity suggests it emerges from the chaotic dance of microscopic degrees of freedom, tiny bits of quantum information we can't yet perceive. Think of it like the pressure in a gas. Individual molecules aren't pushing in any meaningful way, but collectively, their random motion creates the illusion of force. Similarly, gravity might be the macroscopic shadow cast by quantum chaos on the smallest scales. The implications are staggering. If gravity is emergent, not fundamental, it could bridge the century-old rift between general relativity and quantum mechanics. Einstein's theory describes gravity as spacetime curvature, while quantum mechanics governs particles and forces. The two have refused to unify, but entropic gravity offers a path. Spacetime itself might be an emergent structure, built from underlying quantum information. Picture a 3D hologram projected from a 2D surface, except the surface is a sea of entangled quantum data, and the hologram is the universe we perceive, complete with what we call gravity. Evidence for this wild idea might already exist. Dark matter, the elusive substance holding galaxies together, has resisted detection for decades. Entropic gravity could explain its effects without invoking unseen particles. In this framework, dark matter's gravitational pull might be a quirk of how entropy gradients shape space-time in regions where conventional physics fails. Even the accelerated expansion of the universe driven by dark energy might fit neatly into this picture as a natural consequence of the universe's information dynamics. Yet the theory isn't without challenges. Critics argue it struggles to explain precise solar system observations, like the orbit of Mercury, which general relativity nails perfectly. Others question whether entropic gravity can ever be more than a suggestive analogy, but supporters point to tantalizing clues, like the way black hole thermodynamics hints at deep connections between gravity, entropy, and information. The most profound takeaway: if gravity is an illusion, then so is much of what we consider real. Space-time, causality, even the notion of a smooth, continuous universe, all could be approximations of a deeper, stranger reality. It's a humbling reminder that the forces we take for granted might just be the universe's way of keeping its quantum secrets hidden in plain sight. Remember that time you swore Nelson Mandela died in prison in the 1980s, only to discover he lived until 2013, or when half the internet insisted the Berenstain Bears were once spelled Berenstein. These aren't just faulty recollections, they might be cosmic glitches. The quantum Mandela effect suggests that false memories could be more than brain hiccups. They might be scars from collisions with parallel universes where history played out slightly differently. Think of the multiverse as a tapestry of infinite threads, each a separate timeline where every possible outcome exists. Normally, these threads run parallel, never touching. But what if they occasionally brush against each other like sheets blowing in the wind? In those fleeting moments, information could bleed between realities, leaving some of us with memories of events that never happened in this timeline. It's as if your consciousness briefly tuned into a different channel, absorbing details from a version of reality that for everyone else doesn't exist. This idea gains eerie traction when you examine how Mandela effects spread. They're rarely solitary whole groups remember the same alternate past. Take the Monopoly man's monocle. Thousands would bet their life he wore one, yet no version of the board game ever included it. If these were simple memory errors, why do so many converge on identical false details? Quantum entanglement offers a provocative clue. Particles instantaneously influence each other across distances. Could consciousness, if it operates on quantum principles, similarly entangle with alternate versions of itself, sharing memories across realities? The implications ripple beyond trivia. Neurological studies show memory isn't a recording but a reconstruction. Each recall subtly edits the original. Now layer on quantum theory's observer effect, where measurement changes the observed. If consciousness collapses quantum possibilities into real events, perhaps recalling a memory isn't just accessing it, but selecting one version from a superposition of possibilities. Your childhood home's red door might have been blue in another timeline, and somewhere deep in your neural pathways, both colors exist. Skeptics argue this overcomplicates Occam's razor. Why invoke multiverses when brains are demonstrably fallible? Yet the persistence of certain false memories defies standard explanations. MRI scans reveal that when people recall Mandela effects, their brains light up identically to authentic memories, unlike typical confabulations. It's as if the mind genuinely believes these events occurred because somewhere they did. Perhaps the most haunting possibility is that we're all constantly sliding between timelines, oblivious to the shifts. Every déjà vu, every "I could have sworn" moment might be a flicker of awareness, a glimpse of the infinite versions of you living infinite variations of this life. The quantum Mandela effect doesn't just challenge our grip on reality. It suggests reality might be far more slippery and far more interconnected than we ever dared imagine. The universe isn't just expanding, it's thinking. At least, that's the spine-tingling implication when you compare the cosmic web's structure to the human brain. Zoom out far enough, and the filaments of galaxies stretching across the void look uncannily like neurons and synapses in a mind too vast to comprehend. Each galaxy cluster pulses as a node connected by threads of dark matter and hydrogen gas, trading information not through electrical signals but gravity and light. The resemblance is so striking that when researchers superimposed images of brain cells and galaxy superclusters, even experts struggled to tell which was which at a glance. This isn't just a pretty coincidence, it might hint at something far deeper. Consider the numbers. A human brain contains around 86 billion neurons. The observable universe, roughly 200 billion galaxies. Both systems organize themselves into networks where just 20 to 30% of the material forms the thinking structures, neurons in brains, galaxies in the cosmos, while the rest is supportive scaffolding, glial cells in one, dark matter in the other. Both exhibit similar patterns of connectivity, with a few highly linked hubs like the hippocampus in your brain or the great attractor in space, and countless smaller connections branching outward. Even the distribution of matter aligns neurons cluster densely in some brain regions, just as galaxies clump into superclusters, with vast voids between them. But here's where it gets truly unsettling. Networks like these don't form randomly. Whether it's neurons firing or galaxies evolving, both systems follow something called scale-free growth, where small, simple rules give rise to staggeringly complex behavior. Your brain's synapses prune and strengthen based on use, optimizing information flow. The cosmic web evolves through gravitational attraction, matter clumping where density is highest. The parallels suggest that, mathematically, the universe might be processing information on a scale we can barely fathom, not in the way consciousness emerges from our squishy gray matter, but through some grander, more abstract computation woven into space-time itself. Could the cosmos literally be thinking? Some theories take this further than metaphor. Integrated information theory, a leading model of consciousness, proposes that any system with sufficient complexity and causal power might possess some degree of subjective experience. Under this framework, galaxy clusters exchanging gravitational influence could be engaging in a form of cosmic cognition, not with thoughts as we know them, but with a slow, cold awareness spanning billions of years. Imagine the universe noticing itself as galaxies tug on one another, their dance encoding relationships as surely as neurons encode memories. Of course, skeptics argue this is anthropomorphism run amok, seeing faces in clouds writ large. The similarities might just reflect universal mathematical patterns that recur across systems, from river deltas to lightning bolts. Yet the possibility lingers. What if the resemblance is more than skin deep? If the universe self-organizes like a brain, could its structure hint at a deeper layer of reality where information is the fundamental currency and matter merely its expression? The implications rewrite our place in existence. Instead of being bystanders in a dead, mechanical universe, we might be tiny flashes of awareness in a vaster mind, not the pinnacle of consciousness, but brief sparks in an infinite cognitive fire. It's a humbling thought, but also an exhilarating one. After all, if the cosmos is in some sense awake, then every star we see, every planet we discover, might be part of a thought so vast we're only beginning to glimpse its shape. And that changes everything. What if the universe's strangest inconsistencies aren't flaws in our theories, but flaws in reality itself? Take the axis of evil, a spine-chilling anomaly in the cosmic microwave background where temperatures align along a single plane like a cosmic barcode, defying all predictions of randomness. Or the Milky Way's eerie symmetry with the plane of our solar system, as if someone copy-pasted the same alignment across scales. These aren't just statistical quirks, they're cosmic glitches that make physicists whisper about the unthinkable, that we're living inside a simulation, and these are the programming errors bleeding through. The argument isn't as outlandish as it sounds. Every video game has its clipping textures, its NPCs stuck in walls. If our universe is a vast computational construct, why wouldn't it have its own bugs? The axis of evil, for instance, breaks one of cosmology's sacred rules, the cosmological principle, which states the universe should look roughly the same in all directions. Instead, we find a preferred axis, a cosmic north that shouldn't exist. It's like discovering the pixels in your VR headset are subtly aligned to a grid you weren't meant to see. Even more unsettling, the plane aligns suspiciously with our solar system, as if the simulation optimized processing power by reusing code at different scales. Then there's the matter of fine-tuning. The universe's constant gravity strength, the mass of an electron, are balanced with freakish precision. Alter any by a fraction, and stars, chemistry, even atoms would fail to form. Simulation theorists argue this isn't luck, it's design. Just as a game developer tweaks parameters to make their world function, our universe's settings might be dialed in to sustain complexity. Even quantum indeterminacy, where particles lack definite states until observed, mirrors how video games render graphics only when a player looks a trick to save processing power. But here's where scientists split. Some, like Oxford's Nick Bostrom, treat this as a serious hypothesis, proposing experiments to test for computational limits in spacetime. Others dismiss it as unfalsifiable philosophy, a clever metaphor with no way to prove or disprove. Yet the anomalies pile up. The Hubble constant controversy, where different methods of measuring cosmic expansion yield conflicting results, feels like a rounding error between two conflicting subroutines. Dark matter's elusive nature, perhaps it's not a particle at all, but background code the simulation uses to stabilize galactic structures. The debate forces a deeper question. If we are in a simulation, should we even seek to expose it? Some argue uncovering glitches could crash the system or worse, prompt the programmers to hit delete. Others see it as liberation, a chance to hack reality's source code. Either way, these cosmic irregularities don't just challenge physics, they dare us to consider that the universe might not just be strange, but literally stranger than fiction. And that realization doesn't just change how we see the cosmos, it changes how we see ourselves. What if the past isn't just set in stone, but is still being written by the future? The time loop hypothesis takes quantum mechanics' weirdest quirk and scales it up to cosmic proportions. At the subatomic level, particles already defy common sense. Electrons seem to know where they're going before they get there, and quantum states can retroactively change based on later measurements. But what if these microscopic time loops aren't confined to the quantum realm? What if entire events, even conscious decisions, could bend causality into a Möbius strip where cause and effect chase each other's tails? Consider the delayed choice quantum eraser experiment, where a photon's behavior appears to change based on a measurement made after it's already traveled its path. It's as if the particle rewrites its own history to stay consistent with how the story ends. Now imagine that principle applied to larger systems. A scientist in a lab might set up an experiment whose outcome subtly influences their decision to run it in the first place. A writer could pen a novel containing clues that inspire their own future discoveries. These aren't just thought experiments, they're potential glimpses of a universe where time isn't an arrow, but a tangled web of self-reinforcing loops. The math behind this is stranger than fiction. Solutions to general relativity, like Gödel's rotating universe or closed time-like curves, permit macroscopic time loops under specific conditions. In these scenarios, space-time warps so severely that a path exists where you could travel forward in time, only to return to your own past without ever breaking light speed. It's not quite time travel, more like time folding back on itself, like a piece of paper creased until two distant moments touch. Quantum mechanics adds another layer. In these loops, information doesn't just circle back, it can bootstrap itself into existence with no clear origin. Imagine finding a watch on your wrist that you later bury in a desert, only to dig it up years earlier and place it there yourself. Where did the watch come from? The loop has no answer. The implications unravel our deepest intuitions. Free will becomes a hall of mirrors. If your future choices shape your past actions, who's really making the decisions? History might not be a fixed record, but a living document, constantly edited by events yet to come. Even the universe's fine-tuning could be its own cause. Physical constants might be perfectly balanced because a future civilization somehow reached back to tweak the Big Bang settings, creating the very conditions that allowed them to exist. Skeptics argue these loops would create paradoxes too glaring to ignore. But some theories, like self-consistent time loops, propose the universe simply won't allow contradictions. Every action in a loop must harmonize, like a snake swallowing its tail without choking. Others suggest parallel timelines might branch off to absorb inconsistencies, leaving our experience of causality intact while the larger multiverse handles the messy details. The most tantalizing clue might be déjà vu. That eerie sense of reliving a moment could be more than a neural hiccup. It might be a fleeting awareness of the loop, a shiver as time's fabric briefly overlaps. Whether these phenomena are glitches or features, one thing's clear: the universe's clockwork might not just tick forward, it could be winding itself in circles we're only beginning to trace. The idea that consciousness might not be confined to the brain, but could instead be a quantum phenomenon has long hovered at the edges of science, dismissed by mainstream researchers yet tantalizing enough to spark serious debate. If the mind isn't just an emergent property of neurons firing but something entangled with the fundamental fabric of reality, what happens when the body dies? Could traces of awareness persist, not as a soul in the traditional sense, but as quantum information woven into the universe itself? This isn't mysticism, it's a hypothesis rooted in the strange behavior of particles at the smallest scales, where the rules of classical physics dissolve into uncertainty and interconnectedness. At the heart of this idea is a radical reinterpretation of how consciousness operates. Conventional neuroscience treats the brain as a biochemical computer, with thoughts and memories arising from electrical impulses darting between synapses. But some researchers, like anesthesiologist Stuart Hameroff and physicist Roger Penrose, propose something far stranger: that microtubules, tiny protein structures inside neurons, could harness quantum effects to facilitate consciousness. These microtubules might create a quantum orchestra where electrons exist in superposition, dancing between states until collapsing into coherence during moments of awareness. If true, this quantum activity wouldn't just produce consciousness, it could tether it to the universe's underlying quantum field, a sea of potentiality that exists beyond the physical brain. The implications for death are profound. In quantum mechanics, information is never destroyed, it merely transforms. Black holes, for all their voraciousness, may preserve information on their event horizons, as the holographic principle suggests. If consciousness relies on quantum information, could it similarly escape annihilation when the body fails? Some theorists suggest that upon death, this quantum data might dissipate into the environment like smoke from a snuffed candle, retaining some coherent structure for a time. Near-death experiences, those vivid accounts of tunnels of light or out-of-body sensations, could be glimpses of this transition as quantum processes decouple from biological structures and briefly interact with the broader quantum field before dispersing. Critics are quick to point out the lack of direct evidence. Quantum effects are notoriously fragile, requiring extreme cold or isolation to maintain coherence. The warm, wet environment of the brain seems hostile to such phenomena. Yet counterarguments note that biological systems might exploit quantum biology, a field that's already uncovered quantum processes in photosynthesis and bird migration. If nature harnesses quantum mechanics in these domains, why not in consciousness? Even more provocative are experiments like those of quantum entanglement in living organisms, where photosynthetic bacteria have shown signs of quantum coherence. Could the brain, vastly more complex, employ similar tricks? The most mind-bending possibility isn't just survival, it's reintegration. If quantum information persists, could it someday be reassembled, like a cosmic backup restored to a new substrate? This ventures into the territory of quantum resurrection theories, where advanced technologies might one day reconstruct consciousness from its dispersed quantum traces. Far-fetched, perhaps, but consider that quantum teleportation already allows particle states to be transmitted across distances. Scaling this to consciousness would require technologies beyond our grasp, but the principle isn't forbidden by physics. Whether the quantum soul exists or not, the theory forces a reckoning with the nature of self. If consciousness is truly quantum, then identity isn't anchored to the brain alone, but to the universe's hidden architecture. Death might not be an endpoint, but a transformation, a return to a quantum soup where the boundaries between you and the cosmos blur. It's a vision that doesn't just challenge our fear of oblivion, it redefines what it means to be a fleeting pattern in an eternal, interconnected dance. The universe won't last forever, but how it ends is one of the most hotly debated questions in cosmology. Will it fade into an eternal frozen darkness, collapse back into a singularity, or tear itself apart atom by atom? Each scenario paints a radically different picture of our cosmic destiny, and the choice between them hinges on mysteries we're still unraveling. Dark energy's true nature, the shape of space-time, and whether the universe is fundamentally finite or infinite. First, consider heat death, the slow, quiet expiration predicted by the second law of thermodynamics. In this scenario, the universe expands forever, stars burning out one by one until the last black hole evaporates into Hawking radiation. Galaxies drift apart like embers in a dying fire, their light stretched into useless infrared whispers. Space grows colder and darker until every proton decays, every structure dissolves, and the cosmos becomes a featureless sea of particles too sparse to ever interact again. Time loses all meaning when nothing changes. Nothing happens, just an endless, silent void where the temperature approaches absolute zero. It's not an explosion or a collapse, but a sigh into oblivion. Then there's the Big Crunch, a dramatic reversal where gravity finally overcomes dark energy's expansion. Imagine the universe as a rubber band stretched to its limit, then snapping back. Galaxies rush toward one another, the cosmic microwave background heating up as space contracts. Stars and planets merge in violent collisions, atoms are crushed together, and eventually all matter condenses into a singularity, a mirror of the Big Bang, perhaps triggering a new cycle of creation. Some theories even suggest this could explain the fine-tuning of our universe. Each bounce tweaks the constant slightly, eventually landing on a combination that permits life. But the most terrifying possibility is the Big Rip. If dark energy's strength grows over time, it won't just push galaxies apart, it will overpower every binding force in nature. First, galaxy clusters are shredded, then individual galaxies. Stars are torn from their orbits, planets ripped from their suns. In the final moments, atoms themselves are torn asunder, nuclei and electrons wrenched apart as spacetime's expansion exceeds the speed of light at subatomic scales. The universe doesn't just end, it's dismantled piece by piece, leaving behind a scattered, lifeless void where even the concept of distance becomes meaningless. The deciding factor, dark energy's unknown properties. If it remains constant, heat death wins. If it weakens, gravity might pull everything back together. If it strengthens, the Big Rip becomes inevitable. Right now, telescopes like Euclid and the Vera Rubin Observatory are racing to measure dark energy's behavior with unprecedented precision, searching for clues in the way distant supernovae fade or how galaxy clusters distort light. Yet the deepest question isn't just how the universe ends, it's what that ending says about existence itself. A cyclic universe suggests rebirth, an infinite tapestry of beginnings and endings. Heat death implies a one-way slide into nothingness, where even information itself fades, and the Big Rip, a reminder that reality's foundations might be more fragile than we ever imagined. One thing's certain, the universe's final act won't just be an ending, it will be the ultimate revelation of how reality truly works. Einstein famously declared that God does not play dice with the universe, rejecting the idea that quantum mechanics operated on pure randomness. His intuition told him that what appeared as chaos at the quantum-level, particles popping in and out of existence, electrons spinning in all directions at once, wasn't the final word. Beneath the surface, he believed there had to be hidden variables, unseen forces or properties guiding these particles in ways that would restore determinism to the subatomic world. It was a cosmic game of peekaboo, where the rules only seemed unpredictable because we weren't seeing the whole board. For decades, the debate raged. On one side, quantum orthodoxy insisted particles truly existed in probabilistic clouds until measured, with no hidden hand pulling strings. On the other, Einstein and a handful of rebels argued that randomness was just a placeholder for physics we didn't yet understand. The turning point came in 1964, when physicist John Bell devised a way to test whether hidden variables could exist without contradicting quantum theory. His famous inequality set the stage for experiments that would either vindicate Einstein or bury his dream. The results, at first glance, seemed definitive. Repeated tests from Elaine Aspect's groundbreaking work in the 1980s to recent loophole-free experiments showed that quantum particles violate Bell's inequalities, behaving in ways that hidden variables couldn't explain. Case closed? Not quite. A new generation of physicists is probing deeper, asking whether we've been looking for hidden variables in the wrong way. What if they're not local, confined to a single point in space, but non-local, woven into the fabric of reality itself? Imagine a cosmic tapestry where every thread is connected, not by proximity, but by some deeper, invisible weave. In this view, particles might appear random because their hidden variables are entangled across vast distances, operating on rules that transcend classical cause and effect. Recent experiments with entangled particles where measuring one instantly affects another, no matter how far apart, hint that this could be the case. If confirmed, it wouldn't just tweak quantum mechanics, it would upend it, revealing a universe where randomness is an illusion masking a grand, interconnected order. The implications are staggering. If hidden variables exist, even in this non-local form, they could bridge the gap between quantum weirdness and the predictable world we experience daily. Technologies like quantum computing, which rely on harnessing superposition and entanglement, might leap forward with new frameworks to control these phenomena. Even our understanding of free will could shift. What feels like chance might be the subtle influence of variables operating beyond our perception, yet the mystery deepens. Some theories suggest these hidden influences might not even be physical in the traditional sense, but mathematical or informational, coded into the structure of space-time itself. It's as if the universe has a hidden layer of software running beneath the hardware we can see, guiding particles along paths that only appear random from our limited vantage point. Einstein might not have been entirely wrong just ahead of his time. The dice may still be rolling, but they could be loaded in ways we're only beginning to understand. And if that's true, the universe isn't just stranger than we imagine. It's stranger than we can imagine, with secrets hiding in plain sight, waiting for the right experiment to reveal them. What if our universe isn't alone but merely one half of a cosmic pair, a mirror image stretching backward in time from the moment of the Big Bang? This isn't science fiction. It's a serious hypothesis rooted in one of physics' most fundamental symmetries, CPT invariance. The idea is as elegant as it is mind-bending. According to this principle, the universe should remain unchanged if you flip three properties simultaneously: charge C, turning particles into antiparticles, parity P, mirroring spatial coordinates, and time T, reversing its flow. When applied to the entire cosmos, this symmetry suggests the existence of an anti-universe, a perfect counterpart born alongside ours but evolving in reverse, its arrow of time pointing toward the Big Bang rather than away from it. Picture two soap bubbles inflating from a single point, one expanding forward in time, the other backward. In this mirrored cosmos, stars and galaxies might be built from antimatter, with positrons orbiting antiprotons in anti-atoms. Events there would unfold in reverse light absorbing into stars, broken cups reassembling, and entropy decreasing as chaos gives way to order. From our perspective, this universe would be nearly invisible, its influence felt only through gravity and the faintest quantum whispers. Yet it could hold the key to two of cosmology's greatest mysteries: dark matter and the puzzling matter-antimatter imbalance. Here's how. If the anti-universe exists, its particles would interact with ours almost exclusively through gravity, behaving exactly like the elusive dark matter that shapes galaxies. This symmetry could also explain why our universe isn't empty. During the Big Bang, equal parts matter and antimatter should have annihilated each other, leaving nothing but energy. Yet here we are. The anti-universe theory offers an elegant fix. The missing antimatter isn't missing at all. It's just living in the mirror dimension, separated by time's irreversible split at the moment of creation. But how could we ever detect something so fundamentally hidden? The answer might lie in neutrinos, those ghostly particles that barely interact with matter. In this model, the lightest neutrinos could be their own antiparticles, acting as quantum bridges between the two universes. Experiments like the upcoming Ptolemy project aim to catch these particles in ways that might reveal their true nature, potentially uncovering fingerprints of the anti-universe in their behavior. Even more tantalizing, gravitational wave astronomy could one day spot anomalies in the cosmic microwave background, ripples from collisions between our universe and its mirror twin in the earliest moments of existence. The implications are staggering. If true, the anti-universe wouldn't just be a curiosity, it would rewrite our understanding of causality. Events in our future might ripple backward into its past, and vice versa, creating a cosmic feedback loop where time's arrow loses its singular direction. It challenges the very notion of a beginning, suggesting the Big Bang wasn't a start but a symmetry-breaking pivot point in an eternal dance of creation and annihilation. Yet for all its elegance, the theory isn't without critics. Some argue it's untestable, a beautiful mathematical construct with no observable consequences. Others question whether a time-reversed universe could ever develop complexity, let alone consciousness, but supporters counter that the same laws governing our cosmos would apply there, just in reverse. Life in the entire universe might experience time flowing backward relative to us, yet to its inhabitants, their reality would feel as natural as ours does to us. Whether the anti-universe exists or not, the idea forces us to confront a profound truth. Our cosmos might be far stranger and far more symmetrical than we ever imagined. And somewhere beyond the veil of the Big Bang, another version of reality could be unfolding, not as a parallel world, but as the other half of a perfect, timeless whole. Imagine sending a message to a colony on Proxima Centauri and receiving a reply instantly, not after the agonizing 8-year round trip at light speed, but in real time, as if you were texting someone next door. This isn't just a sci-fi dream, it's the tantalizing promise of a quantum internet where communication doesn't travel through space but transcends it entirely. The key lies in quantum entanglement, that spooky connection Einstein hated, where particles instantly influence each other no matter how far apart they are. Normally, entanglement can't transmit information faster than light, at least not according to our current understanding. But what if we've been missing something? What if advanced civilizations have already cracked the code, weaving galaxies together with threads of quantum coherence we're only beginning to glimpse? Think of entanglement like a pair of magic dice. Roll one in your lab on Earth, and its twin on Mars will always show the same number, no matter when or how you roll them. The dice don't communicate, they're just two parts of a single quantum system. Now imagine scaling this up. A network of entangled particles, carefully prepared and distributed across star systems, could act as a cosmic switchboard. Change the state of one particle, and its partner flips instantly, transmitting data without any signal crossing the space between them. It's not about breaking light speed, it's about sidestepping the need for speed altogether. The implications are staggering. A quantum internet wouldn't just eliminate lag, it would enable coordination across interstellar distances in ways that seem impossible today. Colonies on opposite sides of the Milky Way could collaborate on experiments, share cultural updates, or even fight wars in perfect sync, all without waiting centuries for signals to crawl across the void. And if civilizations older than ours have already built such networks, it could explain the Fermi Paradox's eerie silence. Why broadcast radio waves when you're whispering through entangled atoms? But here's the catch: building a quantum internet isn't just an engineering challenge, it's a physics puzzle. Entanglement is notoriously fragile. Any interaction with the environment, a stray photon, a vibration, can decohere the system, collapsing the delicate quantum link. On Earth, we've managed to entangle particles over a few hundred miles using fiber optics and satellites, but interstellar distances introduce cosmic hurdles. Cosmic rays, gravitational waves, and the sheer scale of space threaten to scramble any quantum connection, yet nature might have already provided a solution. Some theories suggest that certain exotic materials like topological insulators or superconductors could shield entangled states from decoherence. Others propose using quantum error correction, where information is spread across multiple entangled particles, creating redundancy that resists disruption. And then there's the wildest idea of all, that spacetime itself might have quantum properties we can harness. Wormholes, often imagined as shortcuts through space, could theoretically form from entangled black holes, hinting that the universe might come pre-wired for quantum communication on cosmic scales. The most provocative question isn't whether we'll build a quantum internet, it's whether someone already has. If advanced civilizations exist, they'd likely abandon primitive electromagnetic signaling for quantum channels. Our radio telescopes wouldn't detect their traffic any more than a tin can telephone could intercept a fiber optic cable. This could explain why SETI decades of listening have heard nothing. We've been scanning the wrong bandwidth. Experiments are already pushing the boundaries. China's MISHA satellite has demonstrated quantum key distribution from orbit, proving entanglement can survive space's harsh conditions. Meanwhile, labs worldwide are racing to build quantum repeaters, devices that extend entanglement's range by linking smaller networks together, the next frontier. Quantum memories that store entangled states long enough to beam them to distant stars via laser or even quantum teleportation, where the state of a particle is transmitted by destroying the original and recreating it elsewhere. If humanity ever cracks interstellar quantum communication, it won't just revolutionize technology, it will redefine our place in the cosmos. Suddenly, the vast distances that isolate us would vanish, and the galaxy might hum with conversations we're only beginning to imagine. And if we're not the first to discover this, those conversations might already be happening all around us, in a language written not in light or radio waves, but in the silent, instantaneous dance of entangled particles. We just need to learn how to listen. We think of the Big Bang as a singular, cataclysmic explosion, a cosmic starting gun that happened once 13.8 billion years ago in a specific point in space. But what if that's only part of the story? What if the universe isn't just expanding outward from a single origin, but is constantly birthing new universes everywhere, all the time, like bubbles endlessly rising in a cosmic glass of champagne? This is the startling premise behind the omnipresent Big Bang theory, where creation isn't a one-time event, it's an ongoing process unfolding right under our noses. Picture space not as an empty stage where the Big Bang's aftermath plays out, but as a seething quantum foam where tiny universes continually pop into existence. Some collapse instantly, snuffed out by the brutal laws of physics. Others survive, inflating rapidly into full-fledged realities with their own unique laws, particles, and dimensions. In this view, our universe might just be one bubble in an infinite froth of cosmic creation, each with its own version of time, gravity, and even logic. The Big Bang wasn't the beginning, it was just the moment our bubble started growing. This idea emerges naturally from some of the most cutting-edge theories in physics. Take eternal inflation, for instance. According to this model, the vacuum of space isn't truly empty but filled with a peculiar energy that drives exponential expansion. Most of this inflattened field remains stable, but occasionally, a random quantum fluctuation triggers a local collapse, a tiny region where the energy drops, releasing a burst of heat and matter. That release becomes a big bang for a new universe, while the surrounding space keeps expanding, creating an endless cycle of cosmic births. It's as if the fabric of reality is a vast, bubbling cauldron, endlessly simmering with new worlds. The implications rewrite our understanding of existence. If big bangs happen constantly, then the universe isn't a solitary entity. It's part of a multiverse so vast that every possible physical law, every conceivable arrangement of matter, plays out somewhere. Somewhere, a universe might exist where gravity pushes instead of pulls, where time runs backward, or where light travels slower than sound. And if these baby universes can bud off from ours, could our own reality have sprouted from another universe's quantum fluctuation? We might not just be stardust, we could be the offspring of a cosmic chain stretching back forever. But how could we ever detect these other universes? The answer might lie in the scars they leave behind. When a new universe pinches off from ours, the event could send ripples through space-time gravitational waves with unique signatures. Advanced detectors like the next-generation LISA observatory might one day catch these echoes of cosmic childbirth. Even stranger, some theories suggest that collisions between adjacent universes could imprint patterns in the cosmic microwave background like fingerprints on glass. Those faint irregularities we've dismissed as noise might actually be messages from our cosmic siblings. The most mind-bending possibility: if creation is continuous, then the distinction between past, present, and future blurs. The Big Bang didn't happen long ago. It's happening right now, in some distant corner of the quantum foam. And somewhere in a universe just beginning its own expansion, scientists might be staring at their night sky, wondering if they're alone, unaware that their entire reality is just one bubble in an infinite sea of becoming. It's a vision that doesn't just challenge our place in the cosmos, it turns the very idea of a beginning inside out. Equations aren't just tools, they might be the universe's native tongue. When physicists scribble symbols like E equals mc2 or Schrödinger's wave function, they're not merely describing reality. They could be whispering in a cosmic language that builds reality. This isn't poetic metaphor, it's a radical hypothesis gaining traction. That mathematics isn't just the language we use to decode nature, but the raw material from which nature is woven. Imagine if the laws of physics are less like rules etched in stone and more like grammatical structures in an infinite, dynamic conversation. Master the syntax, and you might not just predict how particles behave, you could rewrite their scripts entirely. Take Noether's theorem, a cornerstone of modern physics, which reveals that every symmetry in nature corresponds to a conservation law. Rotational symmetry gives us the conservation of angular momentum, time symmetry, the conservation of energy. It's as if the universe is a vast, self-consistent poem where each stanza must rhyme in a specific way. Break the rhyme scheme and the poem collapses. But what if we could compose new verses? Some theorists suggest that advanced civilizations might have learned to manipulate these underlying symmetries, tweaking the grammar of reality to create localized phenomena that defy our known laws, like pockets of space where gravity repels instead of attracts, or regions where time loops back on itself like a Möbius strip. The evidence for this audacious idea lies in the uncanny precision of mathematical patterns in nature. From the Fibonacci sequence in sunflower spirals to the way quantum fields obey gauge symmetries, the cosmos seems to run on code. Even more provocative are anomalies like the unreasonable effectiveness of mathematics, a phrase coined by physicist Eugene Wigner to describe why abstract math, often developed with no practical intent, miraculously predicts physical phenomena decades later. Complex numbers, once deemed purely theoretical, became essential to quantum mechanics. Non-Euclidean geometry, a mental exercise for mathematicians, turned out to describe space-time curvature. It's as if the universe is a puzzle designed to be solved by equations we haven't even invented yet. But how far could this linguistic analogy stretch? If physics is a language, then its words, a fundamental constants like the speed of light or Planck's length, might not be fixed. They could be variables in a higher dimensional dialogue, adjustable by entities who understand the syntax. Some interpretations of string theory hint at this, suggesting that the vacuum of space is a landscape of possible physics, each with different constants. In this view, our universe's laws aren't special, just one dialect in a multiversal Babel. The tantalizing implication: if we ever crack the code, we might not just discover new physics, we could author them. Skeptics argue this veers into metaphysics, but experiments are already probing the edges. Quantum computers manipulate superposition qubits using algorithms that feel more like incantations than engineering. Researchers at the Large Hadron Collider hunt for evidence of extra dimensions potential, characters, in reality's alphabet we've yet to recognize. Even artificial intelligence is joining the quest, with neural networks uncovering novel mathematical relationships hidden in datasets, hinting at a deeper layer of cosmic syntax. The most profound question isn't whether reality speaks in math, but whether we'll ever become fluent enough to reply. If the universe is a conversation, then every observation, every experiment, is a tentative phrase in a dialogue that's been ongoing since the Big Bang. And the next word, it might be ours to choose. From holographic universes to quantum immortality, these 36 ideas don't just challenge our understanding, they tear up the rulebook entirely. Reality, it turns out, is far stranger than anything fiction could invent, and the wildest part, we've only scratched the surface. Every time we think we've got the cosmos figured out, it throws another curveball: particles that remember their future, universes that might be projections, even the unsettling possibility that time itself is an illusion. The more we learn, the clearer it becomes. The universe isn't just hiding secrets, it's rewriting them faster than we can keep up. So what does it all mean for us? On one level, these ideas can feel overwhelming, even dizzying. If the past isn't fixed, if consciousness shapes reality, if we're living in a simulation, where does that leave our everyday lives? But here's the beautiful irony: the more we unravel these mysteries, the more awe-inspiring existence becomes. The fact that we can even ponder these questions, that human curiosity has taken us from cave fires to questioning the fabric of space-time, is its own kind of miracle. Which idea hit hardest for you? Was it the holographic principle, suggesting everything you see might be a cosmic illusion? Or quantum immortality, with its spine-tingling implication that some version of you might always persist? Maybe it was the notion of time crystal structures that dance endlessly in defiance of entropy, or the chilling dark forest theory, where silence in the cosmos isn't emptiness but a survival tactic. Whatever resonated, one thing's certain: the universe is richer, weirder, and more wondrous than we ever dreamed, and this journey isn't over. Every discovery peels back another layer, revealing new questions, new paradoxes, new frontiers. That's the thrill of science, not just the answers, but the endless hunt for them. So keep questioning, keep wondering, and most of all, stay curious. The cosmos has spent billions of years weaving its mysteries. The adventure lies in unraveling them, one mind-bending idea at a time. Drop your thoughts in the comments below. Which concept bent your brain the most? And if you're hungry for more deep dives into the universe's greatest puzzles, hit subscribe, because the next revelation, it might be just around the corner, waiting to turn everything we know inside out all over again. The universe is talking. Are you ready